They couldn't. I think like look and see all these people. A lot. Yeah. Yeah.
Welcome everyone. Let's get started. So thanks for coming today. And so the surprise rain. Hopefully you're not so too wet. So today we're going to be talking about approximate nearest neighbors, and we've talked around this topic a bit already. We're going to kind of give a broader perspective today, and so some sense of where it's so useful and a bit of the historical development of it. Before we get started in the lecture, I want to point out where we are in the schedule, where we've started with kind of a longer, somewhat, so maybe somewhat all over the place discussion on measuring similarity, and we're kind of wrapping this up. This has been extended from the previous years I've taught this course, going in a little bit more in depth in some more modern developments. So we're going to have the lecture today, and then we'll have one more lecture next week, Monday, which will be a new lecture on talking about distances between distributions. So when you don't just have a single object, but you have a set of objects, how do you compare one set of object to another set of object? This has become something I've been seeing more and more so useful within data mining. I've been working in my research on this topic for a while, but I've seen more other people working on it recently. So I'm going to add that lecture for next Monday. And then we'll get into we'll start looking at more techniques in the class. This is kind of building up a lot of foundation, which I think will kind of give you a lot of perspective as we start talking about clustering, kind of streaming models and dimensionality reduction. So those, I think, we'll have a much better perspective on when we talk about those after spending a lot of time thinking about how do you measure similarity or distance between things. Okay, the other thing is the homework assignment due in a week on around locality-sensitive hashing. If you've seen the announcements on Canvas, this one was not as well perfected when I posted it last week, but we've made a few updates to it. It's still a week to go, so I feel I'm sorry to have to do this, but I'd rather kind of admit that I didn't do it properly the first time and update it while there's still time. So we've made a couple updates. I just want to make sure this is clear to everyone. One, we updated the first data set. So if you used as of February 4th, it's called R1-updated. So if you have the old one, you should use the updated one. And then the second question had some other changes. I'm gonna ask you to look at the threshold 0.6 instead of 0.7. I think this will be more informative. And I've clarified a couple of points. So elsewhere, I think we're not written this clearly. So if you have any questions on this, so please ask. But hopefully it's now clear, and you'll get you'll be able to see the signal in these results. This last question 2C is kind of asking you to do something, calling back to the anomaly detection lecture. So where we're you're going to measure the distances between the distributions, similar to how we talked about with the anomaly detection. So that's kind of the point of that part there. Okay, any other questions on this homework assignment? So great. So okay, we're grading homework 2. Hopefully those will be grades will be out sometime this week is our goal. Yeah.
You want us to do 2 CDF plots or just?
Well, they should be 2 CDFs, one for R1 and one for R2, the updated version of R1. And whether you plot them on 2 different plots or plot them together, either way is fine. Yeah, here I'm not asking you to make a direct comparison between them. You're doing the one you're going to generate from part B. Then in part C, you're going to do a comparison. So plotting them all together there might be useful, but you're going to reduce this down to a single numerical value, which will be the Kolmogorov-Smirnov distance. So that's ultimately what I want to do. But if you want to kind of see them all together and kind of see, okay, which one seems more similar to each other, plotting all 3 of them, that you get the 2 from A and 1 from B all together, I think would make sense. Okay. Note that the ones in part A have 500 data points. The one in part B have 250 data points. Okay. And then you look at all pairs of these internally, but the plots of the CDF should be comparable to each other. It looks at it's the Y values between 0 and 1, independent of how many of the data points you have. So that's why it's a useful way to plot and measure these things. Oh, great. Okay. Okay, to clarify, the data collection report, there was apparently on Canvas, I had the wrong date. I had February 12th before. The data collection report is due on Wednesday, the 19th. So after President's Day. We'll talk a little bit more about this next week. I might get someone else to come and talk about some data sets they have available, some resource on campus as well. If you're still not sure if you have the right data set. Again, I have early deadlines for the project, so you get talking about it. And I've seen some of you talking about your projects before and after class, which is awesome, fantastic. That's the point. But they're not set in stone. So if you realize you need to change something at some point later during the semester, that's totally fine. And that's kind of expected. About 10% of groups will do kind of a somewhat major change between when they initially proposed and the final project. But you wouldn't know you would need to change necessarily unless you started thinking about it early. So, okay. All right. So that's the schedule. And then, okay. So today, so the main topic today will be approximate, so nearest neighbors. And so, okay. So the premise today is we're going to have a large set of data P. Okay, so these should think of this as P1, P2, Pn, and this will be some generic type of data. I'm not specifying what this is yet. This could be high dimensional vectors, as we motivated in the last lecture. They could each little p I could be a set, okay, where we might model with Jacquard distance or one of these other distances, right? So these are some objects. We are given a distance, which we're going to care about. Just going to call this generically uppercase D, okay? And so the distance, I'll be able to operate on whatever the spaces these data points are in. So if this is in a space X, right, then the distance is defined as bivariate function to the real values greater or equal than 0, right? So we have so some distance, and the common goal we would like to do is to find the nearest neighbor. Okay, and we're going to define a function for this, which we will use for a bit. We're going to call this phi of p, and then this will be for a query q in this space. Okay, so phi of p of q. Okay, this is going to be the arg min over the set p of the distance between p and q. Yeah, so this is the core thing we're going to be looking at today. Okay, so this, if I say so maybe argmin is not familiar notation. If you've taken 3190, then it should be, but the minimum of the choice over the set p, right, is going to be the point that is going to be the value that minimizes the distance, and the argmin is the argument that minimizes the distance. So it's going to be the point p. So phi of uppercase p, this is an uppercase p here, right, is going to be one of the data points. Okay, so if my data set here are these points in 2D, right, this is my set p, this guy is p1, this is p2, p3, and so on, then I'm going to think of having a query q, okay, and if my distance is Euclidean distance, then I could think of drawing a circle, and there's one point here, pi, right, that is the closest, right? So if I can draw a metric ball, so a distance ball around q, and grow it until it contains exactly one point, well, then that one point right here, pi, is the nearest neighbor. Okay, so then in this example, then pi is going to be phi of p of this query q. Right, so this pi is this pi here. Okay, so this is the nearest neighbor. Again, so this is kind of useful. We talked about slightly different problem before. We want to find the similar set to an object. So we want to have a query object like someone turns in a homework, and I want to check if any of the other homeworks people have turned in are too similar to something, so I have some similarity threshold. But I want to say, okay, what is the most similar homework to this query homework? The one that's most similar, right? I said maybe everyone had to turn in work with a partner, and then your homework should be kind of similar. And I want to guess which query homework is, which one among the set is the most similar. That's most likely the partner, right? And so I want to find the nearest neighbor. Okay, and we'll actually use this nearest neighbor question today within algorithms to find nearest neighbors efficiently. We will pre-compute some stuff using what's called the nearest neighbor graph. All right. So before we move on, I want to say there are extensions of this called the k nearest so neighbors. Okay. So again, I have a query q and a value k, which is greater or equal than 1, right? So now I might think of the 3 nearest neighbors. And so now I want to expand this notion of distance. Okay, so now I want it to include the smallest radius that includes 3 points and instead of 1 point. Okay, so this would be the set S subset of P such that the size of S is equal to K. Okay, and no point P prime in P set minus S has the distance from query to the set prime is less than the distance from query to the set some S, where S is in the set, where this little s is in the set large S, right? So that these are the K closest points. Okay, maybe I'll call this, we'll call this phi of set P, K of Q. All right, so by default, K is equal to 1. But sometimes I want the K nearest neighbors here. Okay. So, and usually if we have algorithm that can find the nearest neighbor, they often extend naturally to find the K nearest neighbor as well. So, okay, so what we want today is to talk about algorithms for how to find the nearest neighbor. And okay, so the obvious algorithm is I have a query point and I'm just going to compute the distance to all the other data points and take the one which is the smallest. Okay, this is pretty kind of the straightforward way to do it. Okay, so the algorithm for the nearest neighbor. So the baseline is check all O of, the size of P distances. We'll say the size of P is equal to N, and return the smallest. The problem is if the size of the data set is very large, then every time I want to answer this question, it's going to take a long time. So often with the field of, think of like data mining, you're given a data set and you want to find something interesting in it. And you might ask a lot of questions about it. And you don't want, every time I want to ask the nearest neighbor query, I don't want to have to spend linear time scanning over the whole data set. Okay, so the more common approach is to pre-process. Okay, so I'm going to spend kind of either O of n time, right? So asymptotically roughly linear time, or maybe O of n log n time, something near linear. So near linear time to build a data structure. Okay, well, I'll call this, what should I call this? A of P, okay? And then I'm going to be able to ask A of P queries, and I want to be able to ask those queries more efficiently, right? So then can ask kind of nearest neighbor queries of A of P so quickly, okay? And what we already had one example of this, okay? So example, if P is in the real numbers, then I can build a binary tree, and then queries are in O of log n time, right? So this is kind of pretty much the best I can hope for nearest neighbor queries. Maybe I can build like a hash structure and say it's constant time, but I'd have to get the exact collision then, right? So if my queries are not exactly matching to my data set, I basically need to spend logarithmic time to do a query. And we talked about this earlier with the triangle similarity, that I could basically find the nearest neighbor in log n time after building a binary tree. All right, so I would like to do something like this. How long does it take to build the binary tree? I probably need to at least sort the data. So something like n log n time, okay? And the space is linear in the size of the data set. Okay, so I'd like to do this more generally, but we have things like we have sets and we have high dimensional data, and I can't necessarily do this trick here. So we're going to kind of talk about this challenge today. And so there are going to be kind of two ways we're going to address, well, there are going to be a few ways we're going to address this challenge. Yeah, so let me start with the classic idea. This is from computational geometry, and this applies to when P is in RD and D is kind of small. Okay, when D is fairly small. So D, think of this will work. So if we are, it's like a big check mark for good if D is equal to 2 or 3 dimensions, and kind of okay if D is equal to 4 up to say 12 dimensions or so. Okay, so and this is kind of a classic idea that was really developed in, I'd say maybe starting in the 1970s, 1980s, 1990s. So it's a common thing. And then, to be honest, most data sets people thought about were not much larger than this. We thought if we had, how could you possibly have hundreds of dimensions? That doesn't even make sense. So that was kind of not, for most people thinking about this, they weren't thinking about high dimensional problems. 4 would be a high dimensional problem. Okay. So, and the basic idea here is to build a hierarchy on the data, kind of extending the binary tree idea. Okay, so I want to take this binary tree idea where I kind of, the nice thing about the binary tree is I had a left side or right side, and I can look at some, make a decision and decide, should I go down the left half or the right half, and then not have to look about the other half of the data again. When I can keep dividing the data in half every step, this is where I get logarithmic runtime. Okay, so I'd like to do something like that in higher dimensions. Now I have kind of data set, let's say in 2 dimensions where this works well. Okay, and I would like to somehow divide the data into 2 parts. Okay, where I could then ask a query. I'm going to pre-compute the data, pre-compute something on the data, and then be able to ask a query later about and know which roughly half the data to look at. Okay, so how do you think I would divide the data into 2 parts in 2 dimensions? Yep. Put on the median. The median of what?
I guess going 2 dimensions.
You could find the median of both directions. Okay, the median, what does the median mean in high dimensions? It's kind of a really, sometimes a strange thing to think about. It's not necessarily in the convex hull of the data. If I find the coordinate-wise median, it's very strange. But let's start with the median just in so just 1 dimension, right? Let's start with this, right? I can take this x direction and I can find the median here, right? Maybe if I just look at the x direction, this is the median. So I'm going to divide the data like, should go through that line, but it should go through this point. And I'd say there's either a left half or there's a right half, okay? And then I have to do this again, right? Then I have to do a hierarchy. Now I have a left half or a right half, and I have to recursively build something, right? So I could take the median again, but the typical way of doing it is actually not to use the same direction. There are a couple of versions, and I'll talk through these, but the most kind of common in practice is what's called the KD tree. Okay, and the KD tree says, well, in the next dimension, I want to take a different median in this half, and then a different median here in, maybe this is the median in this half. So then I recursively, on the left half, I build a median here now in the y direction, and the right half, I also build median in the y direction, but they're not necessarily the same median. If the distribution is kind of shifted up, it kind of adjusts to the data, right? Just same way that a binary tree adjusts to the data in one dimension. And I recursively do this now, okay? Okay, so now, but I'll kind of show a little bit better picture of this first, but let me first say if I have a query, let's say my query is here, then what can I do, right? So how does this work? I want to find the nearest neighbor, probably one of these 2 points. And I'm not going to draw the whole part of this KD tree, but I can say, well, the nearest neighbor is maybe on this side of this line. I'm going to guess that it's on this side of this line and say, I'm not going to search this half. And then I look at the second split in the tree, this green one, and I say, well, it's below the green line. The nearest neighbor is probably below the green line. And I've divided the data set in half every time, so maybe I can finish after log n of these steps, and maybe there's only 1 point left. This is kind of the hope of how this would work, okay? But this is a little bit trickier if, say, the query is here, okay? So now I think the nearest neighbor is on the left side of the purple line for Q prime, okay? But I'm actually pretty close to the boundary. I don't trust it that much, right? And then I do this again. The second line, I'm also maybe I don't know if I'm on the right side of the boundary or not. It turns out the nearest neighbor is in the right cell, but I'm not as confident so anymore. I can't, in one dimension, I can be more confident about it. But in 2 dimensions, I don't have the same sort of guarantees. Okay, so here's kind of a picture with super low resolution that if you're not as close to it as I am, it looks a little bit better. But I grabbed this off the internet someplace, where I have my data set on the left, right? And I'm drawing these splits. This is for a KD tree. Okay, and this is for k-dimensional tree. I'm drawing these splits here, right? This is the first split, and that corresponds with this node at the top that's dividing into the left and right. And then the next level is the median split here and here, right? And these correspond with this is on the left side here, and this is on the right. Okay, and then it's going to recursively split each of these down, right? Between 1, 2, and 3, I'm going to get this one. This is splitting 1, 2, and 3, right? And this is A. B is splitting 4 and 5, right? Splitting 6, 7 from 6 and 7 from 8 is this one here. C and D is splitting this one here, right? And you can see that it's kind of building a tree data structure with some split point, and I can make this decision all the way down. Okay, so now I issue a query. If I have a query here, okay, this is my query. Well, so how would I do this? I would go down I would go, okay, I'm going to go in the right direction. And then I'm going to say it's above the purple line. So it goes down to node. It goes down here because it's above the purple line. So that splits it in the right one. And then it's to the right of this green thing. And I find this point P10 and I measure the distance to P10. Okay. And it says that is a potential nearest neighbor, but I need to check if it's really the nearest neighbor or not. So in order to check, I have to go back and rule out that I didn't cross over any line that I shouldn't have crossed. Right. So first I go and I compare, I go up and compare the split D here and say, well, the distance to P10 is larger than the distance here. So I need to check any neighbor, anything that might be in this tree. So I go down and check, and I have to go back and check in this tree. Okay, and I saw, well, P9 is further away, so it's okay. Then I go back and say, well, let's look at the distance to this purple split, go back up here and say, well, the circle goes over that purple split, so I need to check here, and eventually I find P8. Once I found P8, I've refined my circle, and I say, now I've got a smaller circle. I've got a better option of a nearest neighbor. Okay, so I think this is now the nearest neighbor, and then maybe I know it's not on this side of the split C, and I can go back up, and I say I'm safe. Okay, so I need to go down, I get a guess, and then I go back and I check everything else in the tree. So it's a little bit complicated to get the nearest neighbor. And it's a little trickier. The binary tree in one dimension, I only had to go down once, but this one does a pretty good job of filtering stuff out. And this works pretty well in practice, at least in moderate dimensions. Okay, so this is, and it will, the Python built-in KD tree will give you the exact nearest neighbor. It will work pretty well, and it's been reasonably well optimized. So let's look at, so one thing I want to look at here before we go to the next slide is that if I were to look at this distance to P8, and this circle, maybe it's crossed over this line C a little bit, so there's a small kind of region in here. Okay, so there's a small zone right here that is crossed over that line. There might be a point that's a little bit closer to the query than did I draw this properly? A little bit closer to the query than what I had seen before, but not significantly closer. Okay, and if you remember that the distance I chose was a modeling choice, right? There were a lot of modeling that went into this. And though I may not trust this exact distance exactly, maybe I could stop early if I didn't care about getting the exact best solution. Okay, so this is a picture of what would happen if I have a query. This is a bigger KD tree chart that you can imagine more subdivisions in here. And I've got a query here and I want to approximate the nearest neighbors. Well, if I don't care about the exact one, the amount of backtracking I have to do could be cut down drastically if it's a more complicated picture like this. Okay, so it's more complicated. Maybe sometimes my regions get stretched on these thin sort of rectangles. So I may not want to care about the exact nearest neighbor. I'm okay with something like a nearly nearest neighbor. Okay. Okay, so what we often care about is instead what's called an approximate nearest neighbor. Okay. And I'm given usually some epsilon error, so tolerance. Okay, so think of maybe, yeah, so think of epsilon as being something like in the range of usually 0.05 to maybe 1. Okay, and a 1 approximate nearest neighbor would be off by like might be twice as big. So let me define. So let's say that if phi of P of Q, let's call this minus Q, right? So this is our, or the distance between Q and the approximate nearest neighbor. Okay, so let's call this value the V, which is the optimal distance to the nearest neighbor, right? This is the distance to the nearest neighbor. Then I would be okay with some P prime in P so that the distance from Q to P prime is less than 1 plus epsilon times V. Okay, this would be then P prime would be an epsilon approximate nearest neighbor. Okay, so I'm willing to allow some approximation. So if epsilon is say 0.05, it's off by 5% of the distance. Okay, if epsilon is 1, then I'm off by say like a factor 2. I'm okay with something within a factor 2 of the optimal distance. And so we often look at it turns out it's sometimes very hard to get the exact nearest neighbor, but we're okay with something that's approximately a nearest neighbor. And we're allowing, for instance, we're allowing some modeling error, but the algorithms to be able to run much faster if we can do this. Okay, so we'll talk about locality sensitive hashing again in a few slides. Locality sensitive hashing can only guarantee something that will be an approximate nearest neighbor, not the exact nearest neighbor necessarily. Okay. Let me look. I just want to say one more thing about the nearest neighbor problem. And just so it's a couple things to explain why this is hard. I'll give you kind of two perspectives on this. So if I have a set of points, okay, then I can think of if this is my set P and I have a query point here, query Q, then this is the nearest neighbor, right? This is the closest point in Euclidean distance. And what I can think of doing is pre-computing for every query, what is the nearest neighbor? If I could pre-compute this, then maybe exactly then I could query this pre-computed structure and be able to quickly retrieve the nearest neighbor. This would be what's called I can kind of divide this with these bisectors between these points here. Okay, so it looks something like this. Okay, so this is called the Voronoi diagram. Okay, and if I pre-compute this diagram, which is made up of these edges and kind of these vertices where 3 points are equal distance from each other, if I can pre-compute this and then on a query figure out which cell I lie in, I know what's the nearest neighbor. Okay, so this completely encodes it, and in 2 dimensions, and even in this can lead to a log n time query solution. And in 3D, it can actually lead to some kind of reasonably fast query solutions. The problem is that the size of this Voronoi of the Voronoi diagram of P is going to be roughly the size of P to D over 2. So just computing it and storing this Voronoi diagram, which tells me what is the nearest neighbor in some structural way, is something that grows exponentially in D. Okay, so as I get to higher dimensions, this grows exponentially in the size of the data set. And so this is not feasible in higher dimensions. Okay, so kind of totally pre-computing it it's not going to be possible. Okay, so these KD trees, which have some backtracking, and maybe it's hard to guarantee exactly how much backtracking, work pretty well in practice. There's another approach called a quad tree. Okay, and so this assumes that P lives in a 0 by 1 to the D box. Okay, so I'm going to assume now that there's this 0, 0, 1, 0, 0, 1, 1, 1. And if I'm, you know, maybe this is a box in high dimension, right? But somehow my data lives in this high dimensional box, right? So my data all lives in here. And if it doesn't live in a box like this, I first kind of scale it so it fits in a box. And then I build the data structure. And what the data structure does is it evenly divides the space into these cells. In 2 dimensions, it's got 4 cells. In 3 dimensions, it's going to have 8 cells of each equal size. And each subcell is going to be a box of the same kind of shape as the original one. And I just recursively do this on down. Okay, so this quad tree works pretty well in 2 and 3 dimensions, and most of the theoretical results that have guarantees about how fast I can do approximate nearest neighbors are based on a quad tree way of thinking about it. The KD tree is adapted to the data. The quad tree is not. It deals with the worst case sort of solution. So there's a library called ANN, which I linked to in the notes on the webpage, that looks at quad trees and does approximate nearest neighbors and has very strong kind of guarantees that it will find an approximate nearest neighbor. It's been engineered to work maybe up to 10 or 12 dimensions. It only needs to build the subcells where there's actual data, and that's how it adapts to the data and generalizes a bit higher. Okay. Okay. The other challenge in high dimensions is that all of the approaches we've done so far are kind of using Euclidean distance. Look, Euclidean, start over on that one. Euclidean distance, right? So I've been drawing these things where you have a query, and then I want to find a circle, so there's exactly one data point inside the circle. Okay, but they have been approximating the circle with a rectangle. Okay, because I can spatially subdivide. If I subdivide the space, I have to use rectangles. I can't subdivide a space into 2 balls, right? The balls have rounded edges and they don't really tile the plane, right? So I have to divide it into rectangles. And so the problem is, in low dimensions, this works okay approximation. I'm basically, remember, I want to say if I issue a query, well, the square or the rectangle gives a pretty good approximation of what the circular shape looks, but I've subdivided all the data into exactly one thing. But this works poorly in high dimension. So this is poor in high dimension. D, and I just want to illustrate this with one simple calculation. Okay, so if I look at the volume of a ball, so a Euclidean ball with the radius equals to 1. Okay, do you know what the formula for a ball with radius 1 is in high dimensions? Okay, it's probably not something you would know, so let me write this down for you. It's pi to the d over, it should involve pi, right? The area of a disk in 2 dimensions has to do with pi, right? But it's pi over d to the 2 divided by this gamma function. This gamma function is some weird mathematical expression which shows up here. This is plus 1. So d over 2 plus 1. Okay, and this is approximately, so pi d over 2 divided by roughly d over 2 factorial. Okay, so this is roughly the volume of a ball in d dimensions of radius 1. Okay, and so, okay, we'll come back to how to think about this. Now let's think of the volume of a 0 by 1 to the d box. All right, so I want to think of now the smallest box that can contain this ball. Right, so the side length here, this was a radius 1, so the side length across here is 2. So the volume of this should be easier to write down. It's a 2 by 2 by 2 by 2 box. So this is 2 to the power d. Okay. So what does this look like as d gets larger? Well, this one grows exponentially in d, in the dimension, the volume, whereas the one on the right, this ball, what happens to this as d grows? Does this get bigger or smaller? So yeah, you have the pi to the d over 2, so that grows exponentially, the denominator, but the numerator, but the denominator, d over 2 factorial. That is, remember, that's d over 2 times d over 2 minus 1 times d over 2 minus 2 times d over d minus 3. And so when d over 2 is bigger than pi, then they both have d over 2 terms, but most of these terms are bigger than pi. So as d gets bigger, this actually gets smaller. So it starts getting bigger at the first few values of d, and then it gets smaller. So this actually shrinks as d goes to infinity. So as this gets smaller, so it becomes less than 1 around, say, around maybe 6 or something. Okay, and it starts getting smaller and smaller where this is growing exponentially. Okay, so this area of the box grows exponentially bigger than the area of the ball. So that means even though it looks like a pretty decent approximation here for nearest neighbor, I'm not off by too much if I've rounded by boxes. In higher dimensions, the way to think about it is there are these corners here. These corners basically is the difference in the volume between the ball and the box, and those get exponentially bigger than the volume of the ball. And so most of the stuff's in the corner, and this becomes a very poor approximation. So all these approaches that try to decompose the space nicely into rectangular things so I can look at one coordinate at a time don't really work in high dimensions. It's kind of a fundamental challenge. Right. So okay. So what do we do? What can we do in high dimensions? Just high dimensional Euclidean data. What can we do? So we have to look at all the data, or okay. So Okay, the big breakthrough was that you could do locality-sensitive hashing in a way that extended to high-dimensional Euclidean nearest neighbors. And so I can use this hashing to have things that tend to hash into the same bin if they are similar. And these bounds, how well I can do, and I'll kind of give some ways to think about, write down some version of the bounds and give a way to think about them, did not depend on the dimension of the data. Okay, they worked in arbitrary dimensions. You have to read the data and store the data, which has a d-dimensional coordinate, vectors, but otherwise does not depend on the data. Okay, so I have to define a hash function, and then I can apply the same machinery we did for min hash. Okay, so for d Euclidean, for PQ, which we often write as the norm between P and Q. Okay, so I want a locality-sensitive hash function, and this is going to have two parts. Okay. Okay, the first part is I'm going to first choose U kind of uniform from SD minus 1. Right, so I'm going to pick a random direction. So I'm in high dimensional space, right? And then I'm going to consider all the points that are on a ball. And I'm going to pick one of these at random, which will be U. Okay. Okay, and what this has done, and so now I can take all of P, I can take all of P and project it to, so let's call this PU, which is going to be P1 dot product with U, P2 dot product with U, and so on. What this has done is I've got this direction U, and I've got all these points. This was the origin. And so then I'll think of, I've got this kind of line through here, and this is projected all of these points. So if this is P, then this is P sub U. This is P dot U. It's going to kind of give me a one-dimensional representation along the direction U. So I'm going to choose start with one random direction. And so now points are going to might be close if they're close along this line. If I pick a random direction and the points are close along this random direction, then they're more likely to be close in the higher dimensional space. That's not always true, but the points that tend to be closer are more likely to be close when I project onto a random direction. Okay. One way of thinking about why this would be true is if I look at the distance between Q and P, right? And let's just write down the squared distance. What is this going to be? It's J equals 1 to D times PJ minus QJ squared. Okay, so it's the sum of the squared distances here. And these are along the orthogonal coordinate system. This is the first direction E1, the second direction E2. But if I rotated this coordinate system, the Euclidean distance is the same. Euclidean distance is symmetric to the rotation of the coordinate system. So if I rotated the coordinate system, so instead, this is the first coordinate, and this is the second coordinate, where U1 was the random direction I picked. I can also measure this. Q minus P is going to be equal to the sum of J equals 1 to D of PJ minus QJ dot, sorry, not the J here, just P minus Q dotted on the direction UJ squared. also gives me Euclidean distance. This is measuring in a rotated coordinate system by the UJ. We'll talk about this in the how to think about this a bit more after the spring break, but hopefully you've seen things like PCA before and eigen decomposition. And this means that this first one, I'm adding up these D terms, and I don't know which one is biggest, but this first one is a random in expectation. It's 1 over D of the squared Euclidean distance. Okay, so this first term, so that the expected value over the choice of U, P minus 1, of P minus Q projected on U squared is in expectation 1 over D times the true distance squared here. Because it's 1D of these terms. This was one random direction out here. Okay, so this gives me a good distance in expectation. Now I need to hash them into bins instead of just getting an expected thing. So I have to use the second part. Okay. Let me run out of space here. But now assume I've got this is a direction U, and I've got all my points. These are my points P, and I projected them onto these points in this one-dimensional space. And I've got some query here. So I need to divide them into bins. And so what I do is I kind of divide them into these randomly shifted bins where there's some kind of point that's 0, and there's some offset beta, and this distance is roughly my notion of what the similarity threshold is. This turns out to be the same thing we did for the triangle similarity. Where we want to look at the triangle similarity, which was basically measuring, remember, if the similarity between P and Q was max of 0 and 1 minus the distance between P and Q, right? This was I could write this as for Q, there's some triangle, it's 1 minus the distance up as long as it's here, then this randomly shifting the window into bins gave me kind of a hash function for this triangle similarity. But this is just 1 minus the distance. So if I do the triangle distance, which is maximum value of 1, if things are further than, this region apart, then that's the Euclidean distance in one dimension, right? So if I wanted, so once I pick my random direction U, I can put some bins down on there, and I can use that as the hash function. And again, I can say, let's have a finite number of bins and modularly repeat them, so I have a finite set. The probability of those collisions are small. Okay, so this combined together is roughly, I pick a random direction, U, and then in that direction, I bin the length in that one-dimensional space. And if things fall in these same bins, that's my hash function for Euclidean distance. Okay, and this is one hash function. I repeat different random direction and a different random set of bins, and I get a new hash. Yeah.
Did you talk about how you just?
I have some, so I need to, it has to do with where I set my threshold for what I want to do is similar, right? For nearest neighbor search, I'll get back to how do we get nearest neighbor, but this is where I have some sort of kind of threshold for distance. That is the distance in between the bins, and then there's some offset, and this beta is uniform between 0 and the threshold.
Okay, so are you always doing it down to like one dimension, or is it similar like PCA where you might instead of constructing like one direction, it would be like a plane?
Yeah, so the basic hash function is down to one dimension. But when I use LSH, I need to use these bins together. And when I actually do the bins, what do I want to do? Well, if I combine together two hash functions, what I could think of doing is actually picking two random directions, maybe force them to be orthogonal, and that projects it down to 2D, and then I have a two-dimensional set of bins, and then I have a random offset for those. So that ends up doing the same thing as the binning. So I can create these more restrictive hash functions using these bins. But this is the basic piece. This is the core piece, and then I can use this infrastructure around it to kind of quickly retrieve things which are similar and have a whole bunch of these to kind of make it so the probability of finding any collision is high if it's above the threshold and low if it's below the threshold within some region, right? The whole trick with the binning and getting this S curve. All right, so this is basically how it works. There's actually a trick where called this cross polytope trick. So if you use, I pointed to, there's a library for doing this, which is heavily optimized, called Falcon. Okay, it's a LSH-based nearest neighbor code, and it works for the cosine distance instead of the Euclidean distance, which means that it doesn't care about it only cares about the angle. Okay, hopefully this doesn't bother you too much, because if I'm in high dimensions, then this kind of this S d minus 1, this is d minus 1 dimension. So I've removed one dimension here. But if I look at kind of this piece along here, it looks pretty close. It's a d minus 1 dimensional space, and it's fairly flat for a piece of it. Okay, so if you stare at it, you think, okay, the cosine or the angular distance acts really similar to Euclidean distance in high dimensions. So I can kind of embed something in this space. And it basically means I can skip part of this step if I do that, or I can add this on later. And so their code has ways I can generalize it to Euclidean distance. But like with word vector embeddings, you often care about the angular distance with those. And so these are very related to each other. Okay. And it uses one other trick called like this cross polytope hash, where instead of picking one dimension, it's okay. I think I won't describe that. That gets kind of into the weeds a little bit. Okay. Okay. I want to remind you one more thing about this LSH, to talk about the runtime here. Okay, so first of all, for kind of the nearest neighbor queries, I need to pick the right thresholds. So I need the right threshold that has roughly one nearest neighbor, or a small number of nearest neighbors. But I don't know what this is ahead of time, so I need to do binary search on the threshold until I get basically O of 1, but greater than 0 points. Okay, so if I pick a threshold that's too big, I'm going to get a lot of things that are similar. And if I start reading off of like 20 things that are similar, I'm like, okay, I picked a threshold that's too big. I can look at the data points I've seen so far and say, hey, if there's one with a really small distance, I reset my threshold based on that. Otherwise, I divide the threshold by 2 and I try again. Okay, or I divide it by some constant factor and I try again, or I start really small and then I keep doubling it in size until I find a constant. Okay, so there's some tricks where I have to do some binary search on the threshold, and this adds a little bit of complexity. The other question is, what is the pre-processing and the query time? Okay, so what are the pre-processing query times? For like building a binary tree, I needed n log n pre-processing. I needed to sort the data, and then queries were log n. What can I get here for locality sensitive hashing? Okay, so this you won't know. This is you really need to think about this. So I'm going to have t hash functions total, and I'm going to have b in each bin, and I'm going to have r bins, right? And each this bin will be kind of these super hash, right? And this is where I project down to like a b-dimensional space, think 2 dimensions, and then I can put down a grid of these instead of a 1-dimensional grid, a 2-dimensional grid, and I build a single hash function on top of those indices, and that I can basically interact with each point in constant time if I build my hash table effectively. But each of the R bins, I need to query each of the R kind of these groups of hash, these super hash functions, right? Super hash. I need to query each on a query, and if any of them have an intersection, I count that as something similar. So each of the R bins, all my data, I need to store R times, right? So the pre-processing time is going to be O of n times R. And the query time, I need to query each of these super bins, and there are R of them, and each of them roughly R time, right? There's a few other things I need to do, like with the binary search. So there's some other smaller order terms. Okay, so how big does R need to be? It turns out it depends on the approximation factor, how I want to get this S curve, where there's some threshold, and I want it so that this region inside here, where if it's to the left of this green region, the probability of having a false positive is low. If it's to the right, the probability of missing something, a false negative, is low. So how much approximation factor do I want in this green bin here? Why is this? Oh no, how do I get rid of this? Okay, good. Okay, so it depends on the approximation factor, and let's say this is epsilon. Then there's going to be some. It turns out that. Okay, so let's say it's a little bit complicated to write down. So if epsilon equals 1, so I'm getting a factor 2 in my distance, then I'm going to be able to set R equals to roughly n to the 1, so 7. Okay, so it's a polynomial, right? In general, it's going to be n to the power some rho term here, where this rho will depend on the approximation factor. But if epsilon is 1, so I get a factor 2 approximation, it's roughly n to the 1/7. Okay, so I wanted logarithmic runtime. This is algorithms kind of class you probably learned. Logarithmic query time is fast. Polynomial query time is slow. So what is n to the 1/7 for n equals so 10 billion? Let's say if n is equal to 10 billion, then n to the 1/7 is what?
10.
It's 10, right? So, and if I take something to a small power, it makes it really small. Okay, so n to the 1/7 of 10 billion is going to be about 10. So this is actually can be pretty efficient, even though it's not logarithmic runtime. For a long time, people in computational geometry, which is where I started my research field, were looking at these hierarchical decomposition that said, if we want polylogarithmic runtime, like log to the power 10 or something, then we need like a lot of space, or we need a lot of pre-processing time. It's not really possible. But people weren't looking at, well, what if it was a small polynomial? And so this result with locality sensitive hashing that you could do this was a huge surprise. This was about 30 years ago, this came out, and was very surprising that you could do this quickly, and that this actually is not so bad. Okay, so give a little insight to kind of tie this together. Okay, 10 minutes left. Okay. Okay, any questions on this? I want to tell you the last 5 or so years, people have realized that there's completely other ways to do nearest neighbor search in high dimensions that works 10, 20% better than LSH, but we don't quite know why yet. So, but any other questions about LSH before we move on from this? Okay, there's a new approach called graph descent nearest neighbors. Okay, and this is, I mean, it's not such a very new idea, but the fact it works really well has been kind of a new discovery. Okay, and the idea is I have a data set P, and I'm going to build a kind of a graph on P, and we'll talk more about graphs over the semester. But in fact, it's going to be something like a K nearest neighbor graph. So I'm going to have an edge from Pi to Pj if Pj is in the K nearest neighbors of Pi. Okay, so think of as a picture, think of like this. I've got some data sets P. Okay, and then for every data point, I'm going to connect it to its nearest neighbors graph. For, I don't know what K is here, maybe 3. Okay, and it's not necessarily planar graph, but think of doing this in high dimensions. Okay, so now I'm going to get, so then how the algorithm works, and maybe it's a different graph, but let's start with the nearest neighbor graph is the first idea. And then on a query Q, kind of start at any P and P, right? So I'm going to have a query point Q here, but I'm going to start looking at this P here, some arbitrary P in the graph, and kind of check if any kind of neighbor of P is closer to Q. Okay, so I'm going to look at these neighbors of P. Okay, and I'm going to see, is any one of these closer to Q? In fact, this one is the closest to Q, and move to the closest, and then go to 1, or if not, then stop and return P. Okay, so what I would do is I would go to the nearest neighbor. I'm going to call this P prime. Now P prime, I can now look at its neighbors, right? Its neighbors here. And I see this one is closer, then this is P double prime, and then I look at its neighbors, and maybe this one is the closest to Q, but now nothing else is closer, and it stops. So I build this nearest neighbor graph or some sort of graph on the data that connects stuff. I start at arbitrary point, and I just check the neighbors. If there's a neighbor that's closer, move to the one that's closest to the query, and repeat this until I can't move anymore. Okay, and so it's easy to come up with some counterexamples where this does not work. If I just build the nearest neighbor graph. Okay, there could be big open areas in the middle. I can get stuck in local minimum. And so people kind of dismiss this idea for probably decades. I think I recall being at a conference where someone proposed something like this like 20 years ago and was kind of like, the whole audience got into argument. And then later on, this is now there's a billion-dollar company that's based on this idea. So, okay, there are a couple of more ingredients you need to make this work. Okay, so just doing the nearest neighbor graph does not work. Okay, instead you need to maintain the k nearest so neighbors. Okay, and so as I'm going through this, I'm going to maintain a priority queue of my k nearest neighbors. And if I see anything closer than them, I'm going to update the set of k nearest neighbors. And if one gets stuck, well, I look at the other ones, all of their neighborhoods. Okay, always check kind of all so neighborhoods until you can't improve. Okay, so this kind of keeps you from getting stuck in the local minimum by maintaining a set of, say, 5 or 10 of the nearest neighbors. It doesn't really slow it down too much on these large scale sets. Okay, so this is one idea. The other one is called Hierarchical Navigable Small World, HNSW. And what this does is it builds a hierarchy over the graph. Okay, so you think of having these layers of the graph, and the first layer might be very sparse. Okay, and I'm going to build the nearest neighbors graph here, but it doesn't have all of the nodes. And then the next layer is denser. Okay, and then I'm going to build the nearest neighbor graph on this layer, and then the final layer has all the data points, right? And then I'm going to build the nearest neighbor graph on the full data set here. So then you search in levels. I first search, I run the algorithm on the top level, then I run it on the second level, then I run it on the third level, right? And so the first level navigates to roughly the right part of the graph. And then the second level refines a bit more, and the third or maybe a fourth level finally gets to the ultimate answer. And so doing this kind of allows it to kind of converge quickly. Otherwise, you could have a long spread out graph, and it takes a long time to get from one side to the other. If I build this layers where the top part has only a constant number of nodes, I'm kind of getting this log n improvement. Think of, I'm getting halfway there at each of the layers. I need log n of these steps to get to the last layer, and then the last layer only a constant number of walking. Okay, and this really sped it up. Okay, there are a number of competing algorithms. All the big kind of tech companies have their own algorithm out there. Hierarchical Navigable Small World is one of them. There's one that has some really nice properties called DiskANN. This is from Microsoft. There's a Facebook AI similarity search, FACE. Okay, this one uses some quantization tricks on top of all this stuff that works with GPUs better. So this is Facebook's version. And then there's a company called Pinecone, which a former collaborator of mine built, and it's now has like a market value of like almost $1 billion, right, from being built a few years ago. These are now used inside of this research, so retrieval augmented generation and these deep learning models and stuff. And doing this quickly has found lots of uses in the space. This is kind of the lay of the land. The problem is we can't say much formally about this yet. These algorithms might not find the nearest neighbor or something close to the nearest neighbor. There's a version of DiskANN where we can say something, but that's the slow version of it. It's not the version you would probably use. So this is kind of a space where it's a very active area of research. Can we come up with a version that has the speed, which is say 20% faster than Falcon? But actually we can guarantee that it will actually return something like the nearest neighbor. These work most of the time, but you can construct examples. There's a paper from a year or two ago that constructed examples in 2D where these don't work that generalize to high dimensions. So this kind of I put some notes in the and links in the document online. Okay, there's some kind of ethics topic that I wanted to talk about, and I kept pushing it back. I was hoping I had time today. Maybe we'll find time next week, Monday. But otherwise, we'll stop the lecture here.